Hello everyone, my name is Leif. I took CISC 260 2 years ago and am now a fourth-year student in the SOAT program here at Queen's. CISC 260 was great for me to provide an introduction and a foundation for functional programming. This helped when I went to Microsoft last summer to work with the F# language, which is functional in nature. The skills I learned in 260 provided me with the foundation to read, interpret, and write my own F# code, which was a huge boom during my internship as it led to a full-time offer afterwards. Now, what this means for you is that functional programming is for more than just trivial tasks in class and for learning the theory. It's actually a great asset in industry code for two main reasons. One, even if you don't have to write F# code yourself, you're going to have to read it. If you're on a project where other people have already written F# code, or if it's functional in any language, then you'll be able to interpret it and work with that team because you can read their code and perform it yourself. Secondly, it's in high demand now as a skill set. Many of the current industry workers, programmers that graduated 5+ years ago didn't really use functional programming then, or they weren't taught it to begin with, and now it's simply worn out from their skill set or they don't have it in order to apply it. This is where you as budding computer science students can easily get internships. If you go to an interview with Microsoft or another company using functional programming and say, I took a course in functional paradigms and I know the basics for languages like Haskell, that'll be a huge effort for your interviewer to say, okay, this person's worth a shot. We can teach them F#. We can teach them a skill set which will make them useful during the internship. Now, in terms of why functional programming is good as a language in itself is twofold. One, it's typically a lot shorter than object-oriented code, which we'll see here in a second. And two, it's far easier to debug, primarily because you do it with variables and you simply have static data, which means you don't have to worry about a pointer going crazy, or you don't have to worry about some value which is supposed to be A but is actually B because you changed it somewhere 10 lines up in your code. It's simply much easier to deal with. So considering that, let's get into an example here. I've taken this code as an example interview question from Cracking the Coding Interview, in this particular case 4.1. Now, if you're not familiar with this book, I immediately recommend pausing the video and going to Google it. It is the most important book that you'll have for studying for technical interviews. It's direct from Microsoft, Google, the Big Five, and many others. It'll teach you the questions that you need to know to go into an interview, including those that you'll likely be asked, as well as fun little ways to solve them, either increasing your efficiency when you're at the whiteboard, or helping you work through the problem to try and find a more efficient algorithm to give your interviewer. It'll teach you more than you need to know, and it's a great resource. I highly recommend it. So in this case here, we're taking one problem from the book, doing it in Java, which is the exact solution that the book provides, and in F#. Now you can see the code here on F# on the left and Java on the right. Let's walk through the Java version first. As we can see, this problem is simply about checking for a tree to be balanced or not. If it is balanced, we return true. If not, we return false. You all should have seen something like this in previous courses, likely 203 or 235. In this simple solution, n² time, we simply calculate the height of the node each time we hit it, and then we want to make sure that the difference between the two nodes, the left and the right, is no greater than 1. If it is ever greater than 1, we return false. Otherwise, we simply keep recursing. This is the typical recursive solution that you'll see. Now, if you look at the F# side over here, it looks similar to what you'll see in Haskell and maybe a bit of Python combined. Here we have none in what looks like a guard, which is exactly what this is in functional programming for F#. Here we simply check, okay, if the node is none, or null for Java, then we simply return 0, because we know that it's going to have height 0. Otherwise, we get the height of its children, and we add 1 to it. The typical recursive case that you're going to have for the height of a tree. Now, this code here, personally, I find to be much easier to read, because you have two simple cases, and you don't have to do null checks here, or you don't have to have these big, long returns. It just simply makes it easier to handle. Now, for a recursive case, in the balance check, we have the same style. If it's none, we just give it true, exactly as we did over in the Java code. And otherwise, we do the balance check, and we recurse. So fairly straightforward. The only major benefit here that we have for the F# style is that it's 9 lines instead of 16, which for any programmer is helpful. When we move on to the more complex version of this question, and this is if you were in an interview situation, it'd be worth far more points than simply giving them the n² solution. We're going to use a little trick here, which is just going to be a flag. Now when we calculate the height, instead of simply checking is it 0, 1, or -1 being the difference, we see, okay, if it's greater than 1 in terms of the absolute difference, we're simply going to return -1. And that'll be a flag to us later on to say if we ever have -1, then we can stop the algorithm immediately, because we know we found an unbalanced subtree, which means that the entire tree inherently is unbalanced. Let's look at the right side first, the Java code from the book. It's pretty long for something so simple, mostly because it calculates the height, then checks the height, then does the return. Calculates height, checks height, return, etc. until we have all the way at the bottom where it has its simple is balanced recursion. Now, when we look at the F# code, we have something that looks drastically different. In particular here, when we look at a recursive case for getHeight2, since it's the second version of the algorithm, we have the same base case, where if it's null or none for F#, we simply return 0. Otherwise, we check the heights. Now, what's happening here is that we're actually getting the heights and then piping them forward to a lambda expression, where here we say this is our function, very similar to what you'll have in Haskell, and here's what you're going to do with the values left and right. Here we simply do a matching function, which is similar to what you'll see soon for CISC 260, and then we do the check where if the difference is 1 or less, we can simply recurse, otherwise we return -1, our flag. Then next up, we have our balance check. Same base case as before, but this time we use something a little more complicated. What we do is that we take the children and we pipe them into a fold. Now, a fold is something you'll see soon enough, but essentially it's going to evaluate the current node, it's going to evaluate the left child, and it's going to evaluate the right child, all in one function. It's very convenient, and it's also completely extensible. So if this was more than a binary tree, but a ternary, quaternary, or unbounded tree, then it would have the exact same approach here, whereas Java might get a little more complex. So all we're doing here is that we take a node, so let's say left first, we calculate the height and make sure that our flag doesn't hit where we return automatically, and we make sure that it's balanced. Then we would do the same thing with the right. Similarly, we're going to do our balance check on the current node. Now, one nice factor about this is that there are no variables here. In either the above function or this function, we never have anything that we're mutating. We're only doing calculation. Whereas on the right, we have left height, right height, height diff, and over here as well, we've got the recursive case that we really need in order to do this in Java. Whereas we have the exact same solution, which is easier to troubleshoot and is half as many lines. This is the power of functional programming, and it only gets better as your code scales to larger and larger bases. When I was at Microsoft, I was dealing with a system that was approximately 30,000 lines of F#, but it felt far more powerful than that because its expressivity in this much shortened form allowed it to do much more than the equivalent code in Java. Now, this is a simple example of why F# and functional programming is very beneficial when tackling problems that are otherwise cumbersome in object-oriented languages which you typically deal with. One hidden factor as well, which US students at Queen's will see later on, is that the compiler course, 458, is almost entirely based on this functional style. That is, you have grammars which are parsing, as you might see in CISC 223. It might not look like it at first, but this course will help you immensely in 3rd and especially 4th year of your university degree. If there's nothing else you'll take away from this, what I'd recommend is A. Look at cracking the coding interview, B. Pick up some functional programming skills. Pay attention in 260 and mention that during interviews. It can land you the job that you really need. And C. Keep these skills honed as you go into industry. It'll help you to both refine your own skill set and how you can approach coding, as well as to read and interact with the code from other developers. Overall, you'll be a more effective team member. Good luck this year, and hopefully everything turns out well.